Good morning students, welcome to session 5 on fundamentals of Riemann integrals. So in this session we are going to study some more theorems related to Riemann integrals. So today we are going to study about the continuity of an integral function. Let us take the definition that f of x is a Riemann integral, that is f belongs to R of a comma b, and a function defined by phi of t is equals to integration from a to t f of x dx for all t belongs to a comma b, that is phi of t is equals to, remember this one, this is integration from a to t f of x dx and is called a integral function of f. Take one theorem. The integral function of an integrable function is continuous. An integral function of an integrable function is continuous. Take proof here. Let f of x belongs to R of a comma b. Then the integral function of f is, just now in the definition you have seen here, phi of t is equal to integration from a to t f of x dx for all t belongs to a comma b. It is equation 1. Since f of x is integrable, then implies here f of x is also bounded, because your integral function is bounded here. This implies there exists some constant k greater than 0 such that here mod of f of x is always less than or equals to k. Bounded means it is mod of f of x is greater than or equals to less than or equals to k for all x belongs to a comma b. Let us take some constant. Let c belongs to a comma b and epsilon greater than 0 be given here. Then we have phi of c is equals to, according to the definition of continuity of integrable function, phi of c is integration from a to c f of x dx, and phi of c plus h is integration from a to c plus h f of x dx. This is by equation number 1 here. This is our equation number 1 here. So from the definition we can say here. So here also we have equation number 1, no? Yes. So now consider mod of phi of c plus h minus phi of c is equals to mod of phi of c plus h is integration from a to c plus h f of x dx minus phi of c is integration from a to c f of x dx here. So a to c plus h f of x dx can be taken as here, this is a to c f of x dx plus a c to c plus h f of x dx. This is the property of a definite integral here. A to c to c plus h is nothing but here a to c plus h minus integration from a to c f of x dx. This is the property of a definite integral. If upper and lower integrals are same, then they can get cancelled this from a to c plus h only. So now this is what here these two are same, no? They get cancelled, integration from c to c plus h f of x dx it is. So we know this is less than or equals to, because here mod f of x is less than or equals to k, no? This is less than or equals to mod of k into this one here, k into integration of f of x dx is this is a c plus h upper limit minus lower limit. So it is c get cancelled, it is mod of h into k. So which is less than epsilon if mod h is less than epsilon by k here. So we can take here if mod h is less than epsilon by k, k get cancelled, it is less than epsilon we can take here. Hence phi is continuous at any point c belongs to a comma b. Then this implies here phi is continuous on a comma b, that is the integral of an integrable function is continuous. Let us take here differentiability of an integrable function here. Take one more theorem. The integral function phi of t of an integrable function f of x is differentiable and phi dash is equals to f. Let us take here, let f of x is integrable on a comma b, it is given, and let phi of t is equals to integration from a to t f of x dx for all t belongs to a comma b, be an integrable function of f. This is we know from the definition. So this implies here phi of t is continuous on a comma b. If the given function is integrable, then phi of t is continuous on a comma b. This we proved in previous theorem. So for any c belongs to a comma b, we have what here, phi of c plus h minus phi of c is equals to integration from c to c plus h f of x dx. This we know here. So phi of b minus phi of a is equals to integration from a to b f of x dx. This is studied in previous sessions. So this is equals to here, this is equals to h into f of c plus theta h, where theta is in between 0 and 1. So because here we know this integration from a to b f of x dx is equals to b minus a into f of c for any c belongs to a comma b. So for that we can take here, so b minus a means here this is c plus h minus c. C plus h minus c is here h because c get cancelled. So f of c is here what here? So it is f of c plus theta h. Since f belongs to R of a comma b, this implies f is continuous on a comma b, and this implies here f is continuous on at c which belongs to a comma b. That is limit as theta tends to h tends to 0, f of c plus theta h is equals to f of c, because here h tends to 0, no? So it is simply f of c. So this implies here limit as h tends to 0. We can take here so phi of c plus h minus phi of c divided by h is equals to f of c, because here f of c plus h is equals to, we know here f of c plus theta h is equals to phi of c plus h minus phi of c divided by h we can take here from this. So it is equals to what here? It is equals to f of c by equation number 2 here. This is our equation number 2. So this we can take here as equation number 2. This implies here phi dash of c is equals to f of c here, because it's because what we have here, so this is nothing but here, so this is nothing but phi dash here, this is nothing but phi dash of c here. So from the definition of a differentiation of a function, it is phi dash of c. So we have here phi dash of c is equals to f of c. This implies here phi of t is derivable at c belongs to a comma b, and phi dash of c is equals to f of c. Since c belongs to a comma b is arbitrary, this implies here phi of t is derivable on a comma b, and phi dash of t is equals to f of t for all t belongs to a comma b. Next let us take primitive of a function. If there exists a derivable function phi such that phi dash is equal to a given function f on a comma b, then we say that phi is primitive of f. So that is here, if there exists a derivative function phi such that phi r dash is equals to a given function f. So that is here, if that is what here, if phi dash is equals to f, then f is called a primitive. So that is here, it is nothing but integration here. Integration of f is equals to that is phi dash, no? So phi dash of f, phi dash is equals to f. So then phi is called a primitive of f. Means if integrating on both sides, integration of f of x is nothing but phi. So that is primitive of f. Let us take one theorem here, fundamental theorem of integral calculus. This one is important. If f belongs to R of a comma b and phi is a primitive of f on a comma b, then integration from a to b f of x dx is equals to phi of b minus phi of a. Since phi is a primitive of f on a comma b, this implies here phi dash of x is equals to f of x, because here it is given phi dash of x is equals to f, no? So phi dash of x is equals to f of x for all x belongs to a comma b. Now consider the partition P is equals to a is equals to x naught, x1, etc. up to xn is equals to b of f. Since phi is differentiable on a comma b, take this one as equation number 1, this one. Since phi is differentiable on a comma b, so it is differentiable on each subinterval IR also. So that is subinterval IR is xr minus 1 comma xr for all r equals to 1 to n. Now applying Lagrange's mean value theorem. So we have here phi of xr minus phi of xr minus 1 is equals to xr minus 1 into phi dash of cr, where cr is in between xr minus 1 into xr minus 1 and xr. This Lagrange's mean value theorem is in the last sum here. So this is, we know here xr minus 1 is delta r into phi dash of cr is f of cr, because we know here phi dash is equals to phi dash of x is equals to f of x. So phi dash cr is equals to f of cr by equation number 1. So now here apply sigma. So this implies here sigma r equals to 1 to n f of cr into delta r is equals to sigma r equals to 1 to n. So f of cr is what here? F of cr is phi of xr minus phi of xr minus 1. This one here. Phi of xr minus 1, phi of xr minus phi of xr minus 1 here. So it is equals to, so if you open this bracket here, if you open this bracket, put r equals to 1 to n, phi of x1 minus phi of x naught then plus when you put r equals to 2, it becomes phi of x2 minus phi of x1, etc. When you put r is equals to n, it becomes phi of xn minus phi of xn minus 1. So here phi of x1 remains as it is. No? This is phi of x1 minus phi of x1 get cancelled. Here phi of x2 in the next term, phi of x2 is also there, it is also get cancelled. So lastly only phi of xn minus phi of x0 remains. So therefore here sigma r equals to 1 to n, f of CR into delta r is equals to only phi of xn is b, and phi of x0 is a. So phi of b minus phi of a. So therefore limit as norm p tends to 0, sigma r equals to 1 to n, f of CR into delta r is equals to limit as norm p tends to 0, phi of b minus phi of a. So it is equals to phi of b minus phi of a. Take this one as equation number 2. So but this limit as norm p tends to 0, sigma r equals to 1 to n, f of CR delta r is equals to, we know here this is phi of b minus phi of a is a thing, but integration from a to b f of x dx, because here if you go back here, integration of a to b f of x dx is, because here f of x is phi dash of x, integration differentiation get cancelled, it is simply phi of x. So for substitute upper limit and lower limit, it becomes phi of b minus phi of a. Therefore equation 2 implies here, equation 2 implies what here, phi of b minus phi of a is equals to integration from a to b f of x dx. So that is here integration from a to b f of x dx is equals to phi of b minus phi of a. This theorem is important. Fundamental theorem of integral calculus are very important here. So this is for 5 marks. So if you have any doubt, it's very easy here. You just go through these theorems, and if you find any difficulties in any step, you can ask me at any time. So so what we have studied in today's session? In today's sessions we studied only how many theorems we studied here? We studied only this is how many only 2 theorems we studied. No, one is continuity and another is the differentiability here, and one more is a fundamental theorem of integral calculus. So we studied 3 theorems today. In the today's session we studied only 3 theorems. So thank you for watching this. Thank you.